All right, welcome to Surgical Robotics Lab 3. In this lab, we're going to be focusing on rotation matrices and frame transformations, and we'll do that with 3 activities. The first one, we're just going to be rotating the flange of the robot about the tool reference frame as well as the world reference frame, and we'll compare those and draw some conclusions. Afterwards, we'll take a look at pointing a surgical needle to objects in the workspace of the robot as seen by a medical imaging device with a different reference frame. And then we'll do the same thing in our third activity, except we'll try to constrain the needle to a point in space as if there were an incision, as it would be in a surgical setting. Okay, so in our first activity, we're going to be comparing the fixed versus current frame rotations. So we've got a little theory section here in part 1 that compares the two. Basically, the fixed frame rotation convention means that if you're going to be applying a sequence of rotations about different axes to a coordinate frame, you're always going to be applying them relative to what the axes originally were. So for example, in figure 1 here, we obtain the second set of axes here by rotating about z, but then we obtain the third set here by rotating about where this x-axis is in the first one, but we apply that rotation to the second one. And in the opposite way, the current frame convention will rotate about whatever the current axis frame is. So we've rotated first about the z-axis again, and it's the same as the previous example. But now when we rotate about the x-axis, we're rotating about this one. So we'll end up with a different result as we did up here. And basically in equations 2 and 3, we're claiming that if you rotate about the axes of a reference frame in a specific sequence using one of the conventions, using the other convention in the opposite direction, you should obtain the same rotational properties, or the same Euler angles. So we're going to verify this with the robot by first rotating about the a static frame at the robot's flange, and we'll do that by setting the world reference frame to coincide with the robot's tool reference frame. And then afterwards, we'll compare that to the movement by making rotations about the actual tool reference frame, which will be similar to the current frame convention. So we've got a set of instructions to walk us through that. First, we're going to just remove the robot from a singularity by moving all of the joints to 25 degrees. And then afterwards, we're going to set the world reference frame to coincide with the tool reference frame at the robot's new pose. So in the web interface here, first I've got the move joints command in step 1. And then after I do this command, I'll observe the x, y, z, alpha, beta, and gamma parameters of the tool reference frame at the top right of the web interface, and I'll use those as the parameters to set my world reference frame. So after these 2 instructions here, I should be seeing that the tool reference frame is at all zeros, because the tool and world reference frame are one and the same. So we'll see what happens. We got a delay. I've just put a delay in so that I can pause as I go through the entire activity with you guys. So yeah, it's at 0 after I've set the world reference frame. So next we're going to use the move lin relative to the world reference frame command to provide rotations about first the x, then the y, then the z axes of the world reference frame. And since it's the world reference frame, it'll be fixed after each rotation. So this will be akin to the fixed convention. So I've got 3 statements here using the move lin relative to the world reference frame command. And first I'm doing 10 degrees about the x-axis, 20 about the y, and then 30 about the z. So we'll see what that looks like. Right. So now obviously the flange hasn't moved anywhere in space because we've rotated about it, but we've got new Euler angles in the top right here. So we'll record those and we'll move the robot back to having its joints at 25 degrees. Right, and now after doing that, we'll do that in the reverse order for step 5. And we'll probably see something different, so we'll record that as well. So now I've got the reverse order. I've got 30 about the z, 20 about the x, y, and 10 about the x. So now I've got alpha, beta, and gamma equal to 10, 20, and 30. So that's obviously a bit different. So now we're going to move it back so that all of our parameters are 0 again, so that all the joints are 25 degrees. And now we're going to apply some rotations using the tool reference frame. So this will be step 6. So now instead of using the world reference frame, we'll be using the tool reference frame. And this should be acting as the current axis convention. And you guys can use either the same set of instructions as you did in the first or the second part, just using the tool reference frame, and you'll see that it's similar to one of them. So for example, for me, I've provided x 10, y 20, z 30 degrees in that order. And when I unpause it, we'll see that the robot is now having its Euler angles as 10, 20, and 30 degrees for alpha, beta, and gamma respectively. So we know that the tool reference frame going from 10 to 20 to 30 yields the same result as the fixed frame world reference frame going 30 to 20 to 10 in the opposite axis sequence. So that's something that we're supposed to be observing in this activity. You guys can mess around with it, do different, you don't need to do X, Y, Z, just make sure that you're reversing the order, pick some different angles, and you'll see that you end up getting the same Euler angles backwards with the opposite convention. Okay, so we do have another small activity for part 1, and that is to acknowledge the fact that the macadamic robot specifically uses the X, Y, Z Euler convention. And this is just another important thing to note because the XYZ convention is part of a set of possible actions to take that is completely separate from the current and fixed frame conventions. The current and fixed frame convention is one thing that we have to keep in mind. And then if we look at the Wikipedia article for the Euler angles here, there are actually 6 proper Euler angles conventions that we could use, and 6 Tate-Bryan angle conventions that we could use. The proper angles being a rotation about one axis, then another, and then back to the first one, and the Tate-Bryans being some permutation of X, Y, and Z. So there are 2 conventions that we sort of have to juggle when we're dealing with rotational properties in robotics, and I think that that's why it's a little bit tricky to learn. So it's really important that you know whether you're using fixed or current frames and what the order of axis rotations is. So for the mecha, given a single argument with more than one rotational property, it's assumed that you start at rotation about the X and then move towards Z. And we'll just prove this by providing all of the arguments that we did in the previous step in one argument, and then we'll split them up and change the order. So in the previous step, I used the tool reference frame to first rotate about the X axis by 10 degrees, then the Y by 20, then the Z by 30. So I'm just going to give that to the robot in one command. And then I'm going to put it back to the position where the world and tool reference frames coincide. And then I'll do the Y rotation first, then the Z second, then the X third, and we'll see the difference. So here's what that looks like. Right. So now I've got alpha, beta, gamma equals 10, 20, and 30 as I had in step 6 because we use the X, Y, and Z convention. And then we'll put it back. And then we'll do it in a different order. And we've got a completely different set of Euler angles. Is it done moving? Yeah. Cool. So that's it for part 1. All right, for the next activity, we're given this graphic over here, and we're told that these dots on the workspace are kidney stones that we're observing with the medical imaging device. We're calling the medical imaging device the XRF for X-ray, or X-ray reference frame, and we need to figure out where these points are relative to the base reference frame so that we can move our tool towards it. And this is what you would see in a real environment. If you've got an imaging device that's got a point of interest underneath the tissue, we need to move something that is not operating in the same reference frame as the imaging device to that same point. So there will just be a series of frame transitions or transformations to get there. So I've got this set up over here with the robot as well. We've got some screws in front of the robot, and they'll be in the same position for you guys. We've got the base reference frame of the robot, the tool reference frame at the end of the nephroscope, which has been attached to the robot, and then we've got this imaging device behind it at a separate coordinate frame. So it's this black coordinate frame that we're observing these kidney stones relative to, and then we want to know where they are relative to the base reference frame. And the way that we can do this is using transformation matrices, which have been defined for you guys here in the lab manual. And what enables us to do that is that we know the relationship using the Cartesian and Euler properties of each frame relative to one another. So we can determine where the point is in one if we know it in the other. So what I would do here, given the fact that you know where the XRF is relative to the VRF, is for each of these points here observed in the XRF, I would create a column vector in MATLAB called observed coordinates. And this should be a 4-row column vector because the last one has to be completed with a 1 as seen here on the far right in equation 5. So you'll multiply this by the transformation matrix that you can create in MATLAB. You don't need to use MATLAB, but it would be very useful by subbing in the x, y, z, alpha, beta, and gamma parameters of some of the information that you've been given about the frame's relationships to one another. So you could be plugging in the parameters of equation 9 for that. And then each of the points will be the result of multiplying the observed coordinates by the transformation matrix. So you'll want to verify these with whoever's in the lab with you guys, just because if they're not right, you're probably going to put the needle through the table. One way to be sure that you're right about this is if all of your points are on the surface like you see here, you should probably have a small positive z value that's pretty close to the other points relative to the base reference frame. That way you know that you're staying on the xy plane of the base reference frame. But if you have any questions, ask me in the lab. So yeah, you're going to multiply the points observed by the XRF by the transformation matrix formed relating the BRF and XRF, like I explained. And then once you've obtained all of your points, you can just sort of create offsets in the XY plane so that you can move the needle to the first one using the move propose command, and then you can use the move lin relative to the world reference frame command for the rest of them. So I've given you the Euler angles for the first one for the move pose command, just so that you guys know where to point it, because this had to be determined experimentally. So yeah, this is what that will end up looking like. I'll show you guys the robot here. And don't forget, by the way, to set your tool reference frame to move 190 millimeters down the x-axis, because that'll be down here and it'll have to line up with the tip of the tool reference frame here. If you don't do that, you're going to be telling the robot's flange to go to where the points are, and you're going to put the needle through the table. So that's what it'll look like. You can slow it down, you can add delays between each one. But basically, you've just been given a set of points relative to a different coordinate frame, and the robot has been able to find them relative to its base reference frame. Okay, so in the last activity, we're going to be moving between a couple of the objects in the base reference frame of the robot again, but this time we're going to be making sure that the needle on the tip of the robot is passing through a constraint while it points to each thing. So later on, we're actually going to be looking at making the robot manipulate the needle through a constraint as it goes between points. But for now, we just want to point to two different things while having the needle pass through a constraint at each point. And it's pretty easy to do. So we've got our two stones relative to the base reference frame, here and here. Those are points A and B. And then we've got a constraint at 190, 0, and 118. And that's pretty much right at the tip of the robot. And all we really need to do to make sure that the needle is passing through this constraint as it points to a known location on the base reference frame is to create a parametric line for each point. So this is the formula here, equation 17, for a parametric line. It's a point plus some parameter t multiplied by a vector. And we want this to be a unit vector because we're going to make our parameter t the scalar value that indicates the length of our nephroscope. So I would go to MATLAB for this, but what we're doing is we're determining the location of the flange when it's pointing the needle to each point, which means that we're going to be using the flange as our tool reference frame instead of the tip of the needle in this one. So you'll be setting your TRF back to all zeros. So yeah, I would go to MATLAB just so that you can make the computation nice and easy. But I've got the parametric lines down at the bottom here. So what you would do is you would take the point on the base reference frame, and then you would move backwards. So I'm subtracting 190. You'd move backwards by the t value, which is a scalar 190 millimeters, times the unit vector made from the point on the base reference frame to the constraint that's been given. And you'll do this separately for each point because the flange will actually have to change location when it points to a different stone. And then to determine the rotational properties for each pose, I've given you guys the rotation matrices here for stone A and B. So these are the rotation matrices of the flange, and you'll be using the pseudocode that I've given here to extract the Euler angles. This is just pseudocode, so if you're going to go to MATLAB, you're going to want to change this magnitude to something else. So I've got just the absolute value here. And the reason that we have this big condition here is because we're going to be working with possibly some really long decimal values. So we're just giving it a 0.01 tolerance by saying that if the element in position 1,3 of the rotation matrix is greater than 0.99 and less than 1.01. And remember to convert this back to degrees when you're giving it to the robot. So once you've used the parametric lines to determine the positions of the flange to point to each stone and the Euler angles for each one to pass through the constraint, this is what it should look like. Make sure again to set your tool reference frame to be in line with your flange again. So now when we get to the first stone, we're pointing through the constraint, and we're once again pointing through the same constraint. Okay, and that's it for the lab. For this guy, not a huge report. You're just going to be saving all of your programs, showing your math, and explaining what was going on in each one. And yeah, that's pretty much it. Since these are all in the web interface, just, a text file is okay to be provided for each one, and then make sure that you're submitting some kind of explanation for how you got to the numbers that you got. See you guys in the lab. Good luck.